All right. Any questions now?
But about that, what is that far left one?
Says lat frame or the column V underscore OBS for observer. So basically, how fast an object goes depends upon the observer. There's the problem frame, or what's generally called the lat frame, which was the problem that we were dealing with last week. And that's you're just sitting there, from your point of view, well, actually, from your point of view, you're never moving. But you're looking at this, and this is a situation from, you're in a lab, you're watching this happen. So, the momentum of the 2 kilogram mass is
kilogram meters per second.
those are the units. Look for a number.
Can you say the question one more time?
Momentum. What's the momentum in the lab frame as you're observing this? In the lab frame, what is the momentum of the 2 kilogram mass?
Oh,
That's a 0, right?
That's a 0 there. That's how fast you're moving in the lab frame.
-7 meters per second.
No, not buying that. Oh, that's the total. I'm looking for just the 2 kilogram
Oh,
mass.
just the 2.
8 kilograms? Is it 8 kilograms per meter?
Let's get the units right.
We got kilograms, meters per second.
There we go. Yeah, 8. And the 3 kilogram mass?
Negative.
And then you get the total, which was said earlier, -7 kilogram meters per second. All right, this is what we did last week. Hopefully it has some familiarity to you. So, and I'm gonna put Karen off to the side here. This was going 4 meters per second, and this was going -3 meters per second. No, -5 meters per second. All right, so let's change it up. So imagine that you're sitting there and you're seeing this 2 kilogram mass moving to your right at 4 meters per second. Suppose you also move to the right at 4 meters per second. How fast, what would the velocity of this be from your point of view?
0.
So if you are moving at 4 meters per second, don't repeat units, 4 meters per second, this would be going 0 meters per second. And how fast would that be going? Or what would its velocity be?
-11.
How'd you get -11?
Oh, for the 2 kilogram one?
No, if you're moving at 4 meters per second, it's gonna appear to be going 0.
Yeah.
The 3 kilogram will appear to be going what?
-1 meters per second.
So it's coming towards you, and you're going towards it, and it's gonna go slower than if you weren't moving?
No, it's gonna go faster. So it's -9 meters per second.
Yes, -9. Whatever you do, I subtracted 4 from this one, I subtract 4 from this one. So what is the momentum of the 2 kilogram mass?
0.
This would be the 2 kilogram frame.
How did you get -9? What did you subtract 4 from to get -9?
The -5.
Okay.
It has a velocity of -5 meters per second, subtract 4, you get -9. What is its momentum in the 2 kilogram frame? Okay. And therefore, what's the total momentum of the system? Yeah, -27
Now,
kilogram meters per second.
you got -9 by saying, I mean, we got -27, how? Right,
Momentum. What's the formula for momentum? V. P equals mv. It almost rhymes. All right. Let's do another one. Let's go with the 3 kilogram frame of reference. So you are now moving -5 meters per second. And we've implied it heavily. Actually, should state it to the right as positive. So if you are traveling -5 meters per second, what would the velocity of the 3 kilogram mass be?
0.
And therefore, what is the momentum?
0.
And what is the velocity of the 2 kilogram mass?
-1 meters per second.
No, I would say negative,
When we went from here to here, what did we do? We added how much?
by 5.
Yeah, so you add 5 here.
Oh, whoops.
So what is this momentum?
18.
And therefore, what's the total momentum?
8 meters per second, or kilograms meters per second.
You said 8?
18.
Okay, sorry, I missed the second syllable. All right, so we have 3 different total momentums. Which one is correct?
Huh?
We have 3 total momentums. Which one's correct?
This is a correct one.
They're
Is
all,
there correct?
they're all correct?
Yes, they are.
Certain things.
So when we talk about conservation of momentum, momentum's going to be conserved in all the reference frames. So if we are in this reference frame, I expect -7 afterwards, and this one -27, and this one 18. And matter of fact, if it's a perfectly elastic collision, I expect the kinetic energy to be conserved regardless of the reference frame. Because there is no absolute speed, it's always relative to something, so there's not one reference frame which is given preferential treatment over another. So what we want to do in this method, this is the third method, is we want to find the 0 momentum frame. We want to figure out how fast do I need to move as an observer so my total momentum is 0. Well, it just so happens it's the center of mass frame. So let's work through that. I got space right here. So I know I'm going to do 2, the mass, times 4 minus v. I'm just simplifying the notation. This is the speed of the velocity, sorry, not speed, this is the velocity of the observer, plus 3 times -5 minus v is equal to 0. Since that's the momentum in whatever the reference frame is, if v is equal to 0, then this adds up to -7. If v equals 4, this adds up to -27, and so forth. But I want to figure out what value of v, the velocity of the observer, we get in order to have a total momentum of 0. So it's 8 minus 2v plus -15 minus 3v is equal to 0. I get -7 is equal to -7 minus 5v equals 0. -7 equals 5v. V equals -1.4. This is the 0 momentum frame. And again, that's total momentum. right, questions to there?
So that equation, the masses are the 2 and the 3, and the velocities, which are the 4 meters per second and the 5 meters per second, so I would just add the v. Is there like an equation that doesn't have the numbers in it, or is this specific to this problem?
Oh, generically, well, there is. You'd have M1, V1 initial minus V observer. Plate vectors. Plus M2, V2 initial minus V observer equals 0. Actually, let's go down this route. So this would be V1 initial and V2 initial. If I had to do it, but I'm gonna simplify that, we'll just make that a capital A and make that D. So I've got M1 A minus, and we'll let V observer, or let V equal the velocity of the observer. Again, just trying to simplify the notation. The more subscripts I write, the more apt I am to make a mistake. Plus M2 V minus V equals 0. Let's distribute. M1A minus M1V plus M2V minus M2V equals 0. I'm going to get the V's together, so I got M1A1, oh, sorry, M1A plus M2V is equal to, bringing the two V terms over, M1V plus M2V. So you pause to let people catch up in writing and listening. This equation right here, we've actually done this before, and not with the letters, we plug numbers in. But what is this equation?
Is it a cake formula?
It is not. No, we did this last week. That's for this problem. We did this.
M1A plus M2B equals M1C plus M2B. Where's B? Actually,
It's,
no.
you're in the right area.
M1AC, M1 parentheses, A minus C equals M2 parentheses.
Do you see a negative 1.4 showing up somewhere from your areas from last week?
Oh, there it is. No, that's what we just did. Inertia?
No. Pardon?
Is it like the momentum?
It is a momentum thing. I gotta remember A and B are velocities, so I got a momentum here and a momentum there. Oh, I got a mass times velocity there also. There's momentum here.
Impulse.
No. This is a conservation of momentum, just to narrow it down some.
Perfect elastic collision.
Linear?
Excuse me?
Linear momentum or no?
Well, this is all linear momentum.
That.
That was conservation momentum there. Did I not do it? Did I? Oh. There's the negative 1.4. What problem is that?
That's for this problem. Oh. Perfect inelastic collision.
Yes.
Oh.
This is the perfectly inelastic collision problem. This is the total momentum beforehand. Afterwards, they have the same velocity, so I can just lump the masses as a single mass. This negative 1.4 meters per second put us into the zero momentum frame is the same as the velocity afterwards for a perfectly inelastic collision. If they stuck together, they would be going that velocity. And that is not a coincidence. That is every time. So there are a lot of times on the test that the first question is, it's a perfectly inelastic collision, what's the final velocity? And the second question is, it's a perfectly elastic collision, what are the final velocities? Well, if you've already done the first part, then the second part you've already done what I potentially is the hardest step of this third method. All right, so to get into the zero momentum frame, as an observer, you need to be going negative 1.4 meters per second, which means 1.4 meters per second that way. So what is the velocity of the 2 kilogram mass in the zero momentum frame?
Would it be negative 2.8 meters per second? Or no, it's 1.4, so 2.6.
No, wrong way. Don't forget, you're subtracting the velocity of the observer.
So if you're subtracting the velocity of the observer, would you just do the opposite with the momentums? And so instead of subtracting the 1.4, you would add 1.4?
Yes, you would add 1.4.
So it would be 5.4 maybe?
Yes, 5.4. So it's 4 minus negative 1.4, or 5.4 meters per second. So what is the momentum? Say it again?
10.8 kilograms meters per second.
Yes, 10.8. And what is the velocity of the 3 kilogram mass in this reference frame? It would be, wait, say it again?
Negative 3.6
Yes.
meters per second.
And therefore, what is the momentum in the zero momentum frame? Two ways to solve it.
Would it also be 10.8? Meters per second?
Negative 10.8.
Negative. Negative 10.8. So if you multiplied this times 3, you'll get negative 10.8, but since my total has to be 0, if this is 10.8, that better be negative 10.8.
It just has to equal 0.
Say again?
They have to be equal to 0.
They have to add up to 0, yeah. Now, I would recommend multiplying by 3 just to confirm if you're going through this. another call from the prison. I keep getting phone calls from South Carolina Department of Correction. Some inmate wants to talk to me. All right,
Needs help on his physics homework.
that's right. Oh, I'm so glad you called. Let's talk about momentum. So, what we've done is we've shifted it into the zero momentum frame. So in this frame, what we are seeing is that we have a 2 kilogram mass going to the right at 5.4 meters per second, and we have a 3 kilogram mass going to the left at, well, the left is the negative, so 3.6 meters per second. That's the 3. After the collision, momentum and kinetic energy must be conserved. What is a simple solution that would satisfy that?
Define what?
So that's before the collision. After the collision, I still have to have the same momentum, 0, and the same kinetic energy. What is a simple solution for after the collision where that would happen?
If they stuck together?
No, they stick together, kinetic energy will not be conserved.
They bounce off
Okay.
and continue.
Okay, so we want to fill in the missing pieces there? Okay, so one thing, they don't stick together, so they therefore will bounce off. So this is before